get it, I think.
Yeah, it's not going to be.
All right, sorry. We've got to just forget that.
Okay.
You'll have to look at the screen. Anyway, good big slide.
Yes, so this is actually joint work with Tony and Kerry, as well as Jeff Nichols at the University of Oxford. And I'm going to be talking about the POTS model, where the easing model, which you might know, is a special case. And these models are quite closely related to the exponential random graph models that we were looking at yesterday. And I believe Tony mentioned these models in his talk as well. So we're looking at trying to get scalable computation for image analysis. And the example I'm going to be talking about is with satellite data. I've also applied these methods to three-dimensional CT scans. But the issue is that a lot of algorithms scale very poorly as the number of pixels in the image increases. And in particular, with ABC, you have to simulate the pseudo-data from the model, and if that data is very high dimensional, then your pseudo-data will have the same dimension as the original data, and so that gets extremely expensive. So here we can see with 1 million pixels, it's taking like 50 hours to run the algorithm. And this exchange algorithm that we were talking about yesterday as well, or that Niall was talking about yesterday, scales pretty much indistinguishably from ABC. So they both have this dependence on being able to do forward simulations from the model, which get very expensive for large data sets. So the specific model that I'm going to be talking about is a type of hidden Markov model where our latent states have neighbours on a grid, and so we have the joint augmented likelihood of our data Y and our hidden states Z, and then these hidden states depend on this parameter beta, and beta is the parameter that's hard to infer. So for Z and mu and sigma squared, we can do Gibbs sampling, but beta has this intractable likelihood problem. And beta essentially acts like a smoothing parameter. So when beta is very small, close to 0, we get what looks like white noise. So here we have 3 labels that I've just artificially given 3 different colours. And as we increase beta, we can see patterns emerging in the model. And so clusters form of where the same label is over a larger and larger region. And there's what's called a phase transition in this model, which is there's a value of beta, which is the largest size the clusters can get, where you still have, on average, the same number of pixels in all 3 labels. Once beta gets larger than that, one of the labels will begin to dominate. And it's in this regime, which is called the ordered regime, that best represents the sort of data that we usually observe. So here we might imagine that these green pixels are the background, and these blue and red pixels are the objects that we're actually interested in modelling. And so we're going to have each of those 3 labels is then going to have its own mean and variance, similar to a Gaussian mixture model. but then with this spatial dependence as well. So this is very similar to what we see with the ergom, except we only have a single parameter and a corresponding sufficient statistic. So this is a special case of ABC where in the limit, if we had infinitely many observations and as our epsilon goes to 0, we would actually be able to do exact inference with ABC. But of course, in practice, that isn't feasible. And this sufficient statistic is just the count of pixels that have the same label as their neighbours. And you can see how by counting up those similar pixels, you can then figure out what the value of that beta parameter should be. When you have a very, very small image, so here we have 4 pixels in our image up to 12 pixels, we can actually calculate the normalising constant exactly, and then we can get our expectation for the sufficient statistic given beta. And it has this characteristic sigmoidal shape. And as we increase the number of labels, so 2 labels is the easing model. As we go to 3 labels and then 4 labels, this sigmoid is getting steeper. And as the size of the data increases, we're just scaling up. So there's a maximum value where we have an asymptote. This model is also highly heteroskedastic. When we get to the phase transition point in our model, we have a maximum value for our variance. And then as we increase beta even further beyond that point, the variance actually approaches 0 asymptotically as beta goes to infinity. And we see that both with increasing K and with increasing size of our images. And because these models are an exponential family, similar to what Niall was explaining yesterday, we have some very useful properties that this expectation, so this sigmoidal function that I was showing, is just the derivative of the log of this normalising constant. And from that we can get our score function and then our Fisher information, which is just a single value in this case because we only have a single parameter. And that is then going to be the second derivative. So those plots of the variance that I was showing on the previous slides, they're actually the derivative of that sigmoidal function. So as the slope gets steeper, the variance gets higher. We can show, and we show in this paper that's should go online quite soon in Bayesian analysis, that when beta equals 0, we have a closed form for the mean and variance. And also we know that there are asymptotic values for the mean and variance as beta goes to infinity. So we know the endpoints of this function, and it's what happens in between where things get interesting. The other important thing that we know is roughly the location of the phase transition point, and also roughly what the variance will be at that location. Now, when I say roughly, that's because in order to calculate those things, we need to make some simplifying assumptions that aren't really true for the images that we observe. But as those images get bigger, those approximations get closer to the true value. And so when we have 1,000,000 pixels, these are very close to the exact values that we want. And this was shown in this earlier paper in JASA. One thing that these algorithms like ABC and the exchange algorithm have in common is that we essentially have two different Markov chains that are running in parallel. The main chain is the one that's sampling from our posterior distribution, but then every time you want to do an update to this chain, you need to run this auxiliary chain to convergence to give you some kind of estimate of your sufficient statistic. And so that's looking at ABC from an ABC-MCMC type of framework. But these sort of issues still come up if you do other forms of ABC. The idea that we're using here, and I think there'll be a lot of other talks looking at similar ideas, is that we want to approximate the forward map that goes from our parameter values to our sufficient statistics. And that's the sigmoidal function gives us our first order approximation, and then that smooth function for the variance gives us our second order approximation. And so we want to use this approximation as a surrogate likelihood in place of the expensive auxiliary Markov chain that we would otherwise need to run. And we're going to train this surrogate model using a pre-computation step. And there are a bunch of advantages to doing this. One of the main ones is that if you choose your design points ahead of time, then you can run everything massively in parallel. And so this pre-computation step, we can farm it out to a whole bunch of servers in a cluster, and rather than having to wait for each proposed value of beta, if we just propose betas on a grid or using some other method, then we can parallelize all of that. And then the other trick that we use is you then need some way of extrapolating between those fixed values to figure out what the sufficient statistic would be at your proposed parameter value, or to estimate what that should be. So the first approach that I took was just using a piecewise linear model, which gives a very good approximation to the mean. But when you want to do fancier types of MCMC, you really need that second order information. And piecewise linear, unfortunately, it really doesn't show up on this slide, but it gives a very jagged approximation of your variance. And so most of the proposal mechanisms that could make use of that variance really don't work very well in this framework because your estimate of that variance function is too irregular. So instead we came up with the idea of actually using a deterministic approximation where we had a look at the characteristic shape of this variance function and realized that we could approximate it quite well using this exponential of the square root of the difference between beta and that phase transition value of beta. And that then gives us still a piecewise function, but it's only piecewise in the sense that we have one completely smooth function for beta approaching the phase transition from the left, and then a different smooth function with different parameters for beta approaching the phase transition from the right. And this then gives us an approximation. So we now don't just have an approximation for the mean, but we can also approximate the variance. So these blue dashed lines give us, I think that's 3 standard deviations around the mean of that function. And you can see that all 3 lines are all meeting together in that asymptotic limit as the variance goes to 0. And it's much clearer to see when you actually subtract out the mean. So this is just looking at the difference from the mean on the right-hand side of this plot. So these black dots are our simulations that we've done. I think this is 37 fixed values. It looks like it's more, but I think that's what we're showing here. And then we've got, for each one of those values, we've got 5 simulations, and with 3 standard deviations, we've got a pretty good bound on what those simulated values would be. And so rather than doing more simulations at each iteration, we can just use this approximation instead. So this then comes into our MCMC algorithm. The only real difference here, so step 1 is our pre-computation step. Then we need to fit these functions and estimate the parameters of these functions. So I use stan for fitting the surrogate model and getting posterior distributions for those parameters. And then when I'm running the MCMC algorithm, I just use that mean and variance from my surrogate model to give me a truncated normal approximation to the distribution of the sufficient statistic. And then I can use that directly in the Metropolis-Hastings ratio. So for a simulation study, we can see that quite often with ABC MCMC, you'll find that it gets stuck in certain regions of parameter space. And the reason for that is that in standard ABC MCMC, you need a single value of epsilon, your ABC tolerance, for the whole range of possible parameter values. But in a heteroskedastic model such as this one, there is no single value that's uniformly good across the whole parameter space. And so that's where ABC runs into a lot of difficulties. Whereas with our deterministic approximation that I call PFAB, we're able to converge even for images that are in that ordered regime. So when we're past the phase transition point, we can still get good estimation. And now for a real data example, so here we have Brisbane, QUT's somewhere around here, and we've got 1 million pixels here that are these normalised difference vegetation index. And so the goal of this analysis is we want to label all of these 1 million pixels as being one of 5 different types of ground cover. And that goes in increasing order of value. That goes from water to the built-up urban areas to the suburbs. And then we have 2 different labels for the forest and other greenery around the city. And this is our labelling with 5 pixels. So you can see we pick up the Brisbane River quite well. This is Gardens Point here in green. And then in black, this is the built-up urban areas. And in grey around that, we have the suburbs.
Size of the landscape pixel on the ground, is it?
30 metres by 30 metres. So you won't pick up individual buildings at that scale. And so each pixel is more like a mixture of things at this scale. Yes. Yeah. Yes, so industrial areas are going to show up as well, like that. That's right. So it's based on the reflectance, so how much heat is radiated off the buildings. And that's why if you've got big concrete buildings anywhere, then that's all going to be labelled with that. So that's where you don't want to be when it hits 40 degrees. You want to be in the green areas, not in the black areas, because it's just going to reflect heat at you from every direction. Yes, yeah. So then this is our 5-component mixture of Gaussians, and this is a comparison. So here we have ABC has this characteristic flat. When you use the hard threshold of epsilon, you get this flat posterior shape, whereas this is the approximate exchange algorithm in black. So we're using that as like a gold standard for what the posterior should actually look like. And our blue dotted line is reasonably close to the black line, so we're quite happy with that approximation. And then we get a massive speed up. So one image is taking 1.4 hours. Yeah, so it's gone from about 100 hours for ABC, or the exchange algorithm, to only 4 hours using our surrogate model. And the reason that we're trying to do this is so that we can use this smooth function to improve our proposals and then also get more efficient mixing in our MCMC algorithm. And there's potential that this could be extended to higher dimensional problems as well. Thanks, everyone. I'll take questions.